Hi, I'm AJ Piergiovanni from Indiana University. I'm going to present some of our work on using video neural networks for sports analysis. With video neural networks, a primary task is recognizing activities in videos. This can be as simple as giving a clip of various activities and trying to classify what's occurring, or this can be more complicated when we're given a long continuous video and we want to detect what's happening, as well as localize the start and end times of the actions. Standard methods using this rely on convolutional neural networks. These networks are able to learn different representations and information to recognize the activities.
Pitch out of the ballpark that he saw from Dallas Keuchel.
One of the works we created was the MLB YouTube dataset, and this dataset contains 20 baseball games from the 2017 baseball season, which has over 42 hours of video. This allows us to recognize various activities in baseball using this dataset. One key challenge in baseball is that the difference between actions is very small. If you're trying to classify actions such as playing basketball or swimming, there a single image is often enough because a pool looks very different from a basketball court. But in baseball, the difference between swinging and bunting or getting a hit and not getting a hit are often very, very small. And this makes it challenging for computers to recognize these actions. For example, here we have a hit video, but we can also do things like use the network to determine how fast the ball is thrown. For example, in this one, the pitcher threw at 96 miles an hour. We can also try to learn pitch type classification, such as fastball versus curveball or slider, and so on. And we also have the ability to recognize these actions in very long continuous videos. However, as I suggested before, differences between these actions is very small. For example, in the middle and the right images, the batter is swinging or bunting, but they look very similar from just a single image, and it's challenging for the computer to know which one is happening. Further, determining things such as the difference between a ball and a strike is very, very difficult, even for humans, especially from video where its camera is far away. Oftentimes, oftentimes we find the neural network cheats and looks for the umpire's signal after the play. Here are some example clips from the dataset showing the different actions in the baseball games. As you can tell, the differences between swinging or bunting and balls and strikes from this broadcast camera view are very similar and very hard to tell apart. Further, there are some actions such as hit by pitch which very rarely occur, leading to limited data to learn from, making it challenging to recognize. Our dataset is fairly large, having thousands of examples of the most common actions. However, things that are more rare, such as bunting and being hit by pitch, we have only 10 to 20 examples of, making them quite challenging to recognize. Due to the challenging nature of this problem, the way we propose to recognize these actions in baseball videos is to decompose the actions into what we call sub-events. Here, a larger action, such as a push-up, can be broken down into smaller parts, such as moving down towards the floor and pushing back up. By decomposing actions into these smaller parts, we can then recognize more complicated structures. To do this, we use specialized layers within the neural network. These layers we call temporal attention filters, allow the network to localize different sections of the input video to recognize the smaller parts of the action. It can then combine these smaller parts together to get a good idea of what's happening to recognize the more complicated actions. When we try this approach out on the MLB YouTube video clips, we find that we can get quite good performance with about 60% accuracy. Using just the standard neural network and then averaging over the frames gives about 40 to 50% accuracy. By adding in more complicated structures such as LSTMs or temporal convolution, which allows some level of understanding time, performance improves. But when we use our super event approach, we can get the best performance, showing that by learning these different parts of actions is beneficial, especially in these baseball videos. We can further look at this and see which actions the network is succeeding at recognizing and which ones it struggles to. For example, things like hitting, it's very accurate, but detecting a foul ball is more challenging. Similarly, determining the smaller things like bunting or hit by pitch, the network really struggles as those have the lowest accuracy. But things like strikes and swings and hits, it's over 90% accurate for. We can also look at the intervals the network is choosing to focus on for these different actions. And you can see that for most of them, it focuses near the beginning where the start of the pitch occurs, and then also looks towards the end where things like the batter's motion or the camera view change will indicate if it was a hit or if the player was hit by the pitch. We can also use this approach to determine the pitch speed purely from the video. While systems like radar is far more accurate, using just video still gives quite reasonable performance, so we can get within about 4 miles an hour of the actual pitch just from the simple broadcast video. Again, we can see the frames it focuses on here, and it tends to focus on different intervals so it can capture different speeds depending on what happens in the video. The even more challenging setting is recognizing the pitch type just from a video. State-of-the-art systems for this require first tracking the ball and sometimes even determining the spin of the ball before it can classify the pitch. Here, we're using just the broadcast video and trying to have the network recognize it from just that. Again, what makes this very challenging is that professional pitchers' motion throughout the pitch is the same or very nearly the same depending on, or no matter what pitch they throw. This is by design because they don't want the batter to know what's about to come. The only way to tell the pitches apart is to follow them through their trajectory and see where they end up and how they move. Doing this from just broadcast video is quite challenging. To do this, we first used OpenPose to detect all the joints and body parts of the pitcher. We can then track these through time and use the pitcher's motion as some input. We also allow it to use the RGB input to further enhance its features and allow it to track the baseball better. And by combining both of these, we can accurately classify the pitch about 35% of the time. As this is a very challenging problem, this is decent performance. Another key challenge in analyzing baseball videos is that we first have to find the clips. In the previous example, we assumed we already had clips of the pitches and the hits and so on. But in the more realistic setting, we just have a video of a baseball game and we want to determine what's happening and when it's happening. To do this, it requires processing all the frames of the video and understanding how things are changing over time. And then once we can make a decision for each frame of the video, we can use those decisions to localize where the certain actions are occurring. Again, we can use this approach on the MLB YouTube dataset. However, the performance drops down to about 40% accuracy here, as it's more challenging to recognize the start and end times of these various events. Here we show some examples of a ball strike, a swing, a hit, and the foul ball, and our model's predictions. As you can see, it does pretty well localizing when the swings and hits occur. It also does well for the other actions we show, such as a foul ball in this example. Overall, this system is quite accurate and able to take any baseball video input and then produce an output of this specific clips where the certain actions occur. Now that we can extract clips from videos, we can do more interesting things, such as determining if a pitcher is injured or not purely from a baseball or purely from videos of the pitcher throwing pitches. This is a very important problem, as in the MLB, injuries are extremely expensive, especially since pitchers are highly paid, and if they're injured, they miss out on a lot of games. However, the difference between a pitcher throwing when he's healthy and when he's injured is almost impossible for humans to see. For example, in this video below, the left is an example of a pitcher throwing a pitch early in the season, and on the right is an example of him throwing a pitch later in the season, but this was the last pitch he threw before he had to have Tommy John surgery. But watching it, it's impossible to tell the difference between the two. He looks equally healthy to the human eye. So here we want to explore if we can use these neural networks to predict if a pitcher is injured or healthy purely from video data. To do this, we first started with just simple video clips, but we found that the model liked to overfit and make bad predictions based on other features, such as maybe the pitch count shown in the video, or the jersey the pitcher is wearing, or maybe there was fans wearing colorful t-shirts in the background, or other things that can indicate whether the pitcher was healthy or changing the game setting. We wanted to kind of remove all of these other features and just focus on the motion information, so we changed the input. Instead, we used Optical Flow, and Optical Flow is a feature that shows the motion without any appearance information. So it tracks how things move over time, and then we cropped it to just the pitcher. This allowed the model to focus just on how the pitcher is moving over time to give a feature for recognizing injuries without any of this other data that could change. We then conducted a variety of experiments across pitchers and across the common injury types in the MLB. And we found, surprisingly, that using these models, it was able to recognize injuries from pitch data quite accurately. However, what's really challenging is determining why the model is making this prediction. Using it currently, it makes a single prediction, like if the pitcher is healthy or if the pitcher is injured. And if it says the pitcher is injured, that's all it says. And using that in the real world is not likely to be useful, as a coach can't just tell a pitcher the computer said you're injured. They aren't likely to listen or be happy about that. So finding a way to make this more interpretable so the model can say why there's an injury will be much more useful to coaches and players and could better protect their health. Another thing to add to this is that pitches aren't independent. Generally, with pitchers, the injuries are due to overuse. So modeling these pitches over time to capture how their form is changing or showing injuries would lead to a better model and more interpretable decisions. Finally, there's other tasks that we can do with computer vision, such as tracking the ball, and then we can determine the spin rate and orientation of the ball. We can track pose of the batter and kind of monitor how the swing of the batter is changing over time, and so on. All of these things we have been able to do with video neural networks applied to baseball videos. So thank you for your attention. Here's a link to a bunch of the code, data sets, and papers I mentioned in this talk. Thank you.